Hi, my name's Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. Today I want to ask the question, what really is new fire fuel? I want to do this by exploring real data from experiments with the aid of Dr. Alexander Parkhomov's reaction tables. Now, in a previous presentation, we have shown Dr. Parkhomov's reaction tables converted into an SQL searchable online form by a man from New Zealand who'd volunteered his time. Thank you very much. His name is Philip Power. Well, since then, we learned a lot. We did a presentation with this, and another guy from Europe called Denis Lamote has produced this site, which we are hosting on fuzzfist.org. That's FUSFIS.org. And this doesn't just do the 2-to-2 nuclide reaction tables, it also does the fusions and the fissions. So we have the 2-to-2, the fusions and the fissions, and it also shows the stable isotope. So if we click here and we say, right, I want to see how many isotopes there are of tin, I type in SN, and it shows me all of the isotopes of tin, which there are quite a lot, and the relative natural abundance. So we can see here that most of it is 120A. Then if we wanted to say, I don't know, let's try another one that has a few isotopes, osmium here. So we've got 41% on 192 osmium. So that gives you the isotopes that are stable. There are some non-stable isotopes in this data, plutonium and the common fission products from uranium fission, which is 90 strontium and 137 cesium. In addition, there is 60 cobalt. So that's all in there, and from each of these tables you can access the other tables. So if we wanted to do some reactions and look for, I don't know, let's look for silver. So here I put silver in element 3, and it says that there are 3,624 reactions that produce silver in element 3 column. Perhaps there is some that produce in the element 4 column. Yeah, 2,460 in the element 4 column. And it gives you the relative energy yield from those. Actually, in the table of stable isotopes, it also shows you the energy contained within that particular isotope. And if it has an asterisk, that means it is radioactive. Okay, and then there's fusion. So let's try the classic one here, aluminium fusing with aluminium. And we get 227 aluminiums, making iron 54. Very, very powerful. Let's see what fuses to iron. There we go. So there's all of these different reactions here, 42 reactions that are straight fusion to iron. And let's look at fission. So let's try something that's quite heavy. Let's try mercury, and let's see what we get there. So there's 23 fission reactions, which go to, here we go, calcium and neodymium, and so on. So this is very, very powerful. You can type in your A and your Z numbers, constrain things by putting element at 1, element 2. Likewise with two nuclides. So for instance, if we have, I don't know, carbon and oxygen here, and we fuse those, this gives us our various options that we can get here: helium, magnesium, hydrogen, aluminium, carbon, oxygen, with a shift in isotope, and so forth with the relative energies. So really this is incredibly powerful. We're hoping to add in the ability to sort results by not just by the maximum MeV yield, but also by the isotope abundance. So ideally what I would like is something where you put in the elements that you have in your fuel or your ash, or both, and it uses these various tables and statistics based on the abundance, natural abundance, to try and statistically work out what the reaction paths that are most likely given this data, although this is, as Alexander's quite aware, a very strong simplification of what may actually be going on underneath. Okay, so I want to take you through the presentation for which I've used that data. And I just wanted to first bring up this chart, which is, for me, one of the most interesting things about nature and elements, and that is the atomic abundance in the Earth's crust. And what we see here is these elements like oxygen, silicon, calcium, potassium, iron, titanium, manganese, magnesium, so on. These are what are called the rock-forming elements, and they're fairly light elements, and they are abundant, and they make up a good proportion of what the crust is. Then down here you've got the super rare ones like your osmium here, and your gold, and your platinum, iridium, rhodium, palladium, ruthenium, tellurium. So these are your rarest metals. Then the other interesting thing is this, which we've discussed before, is that there is this PB here. And why do we get PB? Now, I've argued that the active agent, if there's a lot of energy being fed in, or it's capturing a lot, harvesting a lot of energy, then the active agent will assemble and assemble and assemble until it gets to lead, and if it's still got more energy being fed in, it'll push beyond lead. And then actually the reality is that lead 204 is the heaviest stable element that is basically created this way, whereas 206, 7 and 8 are decay products from heavier elements. Okay, so you can push to bismuth here by adding H or D to isotopes of lead, but that is technically radioactive. But the other elements beyond this are all radioactive, and they will drop back down towards lead. So in part, my view is that the pushing up here to lead creates a lot of lead, and we've seen this in the echo fuel processing of Suhas Ralkar, but it's also there in Adamenko's work and with the work of Mark LeClair. He sees a lot of lead, but in nature we see a lot of lead. And is it because when all the elements were formed that make up the crust, there was also a lot of radioactive elements, and they step back down. So you've got a push up and a decay down. So you get a lot of lead in the crust. So this is very interesting. Oxygen is way up here for the amount, and lead down here, and we'll come back to that in a little while. So then there's the George-Ohsawa cycle, and I've talked about this a lot, and we replicated the data that this kind of produces in a NOVA reactor last year. Now, at the time, I dismissed that because I could find reasons potentially for most of the elements that were in there, and so because we were using charcoal and so forth with the first test that was conducted in Budapest. However, I will present this later as part of ODO, there is extremely strong evidence that it did actually work first time, and it is not just the evidence of the SEM data as presented previously that leads me to believe that this is actually happening. But the interesting thing that is going on here, and this was replicated by a number of different people, is these elements happen to be mostly these elements. So this process is producing these rock-forming elements. And what I've done is I've looked at these various reactions, and I've gone through each of them, and so carbon plus nitrogen, so carbon plus nitrogen goes to, click here, open a new tab, let's try that, yes, okay. So there we go, carbon to nitrogen goes to aluminium, so there's two potential options. These are the two outputs and with the various isotopes. And interesting, the only ones that are net positive are going to these two isotopes, both forming 27 aluminium. It's a single isotope that it steps to. Let's try a different one. Now, the one I want to try now is scandium, and there's two paths to scandium. But the interesting thing is that scandium was not observed in Dr. George Eagley's research over many years. And why might that be? Well, firstly, let's have a look. We'll open this in new tab. So there is a reaction here. For instance, oxygen and aluminium goes to scandium, and that you would think, why isn't that appearing there? Well, I want to return to this chart, which is the atomic volume chart, which I've been talking about because I have an understanding that it may be due to a sort of implosion technology. And if you actually look where scandium is, it's actually somewhere here. It's not marked. We've not observed it, and no one else has observed it. But scandium is here, which means it's got a lot of atomic volume. So you're stepping from the fusion of whatever it was. Let's have a look. There's a fusion of oxygen and aluminium here. So aluminium is here and oxygen is here. So they have relatively low atomic volume to scandium, which is like way up here. And it almost doesn't want to do it, I guess. And if you actually look, if you take scandium and fuse it with oxygen, you go to copper, and that's all the way down here. If you fuse it with nitrogen, you go to nickel, and that's all the way at the bottom of this atomic volume area. And with hydrogen or deuterons, you get titanium, which is all the way down here. So it might just be that it's, and Alexander Parkhomov recognized that this data tables that he has, they're only looking at 2 to 2 or fusions of 2 to 1 or 1 to 2 fissions. He recognizes that this might only be part of the story. And here's a practical example where the real data taken over many years points to the fact that you don't see scandium, and could it be because it has a high atomic volume and because it's in this sort of box and it can't really expand out or whatever. It kind of wants to fuse with something else. So you're getting 3 going to 1 nucleon, and overall it takes a lower atomic volume. So if you've got titanium here, it's lower than scandium, and if it goes down to either copper or nickel, those 3 atoms would be below in atomic volume aluminium or oxygen and the nitrogen from which it is composed. So it's very favourable for it to not stay at scandium. So moving on, I looked at other reactions here that lead to iron and to nickel. These are reactions where we are looking at interacting the aluminium and the silicon, and the aluminium and the phosphorus, and the silicon and the phosphorus. Actually, aluminium and phosphorus, the most energetic reaction leads to 4 helium and 54 iron, and both of these have very low atomic volume relatively. They've got a big reduction in the amount of the physical vacuum they distort. Now, I want to take this concept into the explanation of the echo fuel and why it may be working. So here's the echo fuel processor. I'm going to blow this up into a new tab so you can get a better look at it. So into this water, deionized water, was placed carbon, titanium, and nickel. And these here and here and here are 3 19.46 kilohertz resonant 1.5 kilowatt ultrasonic horns, and they are cross-axis vibrating into this, and there's a sealed top that goes down on this container. And therefore, they're putting a lot of energy in. And Suhas Ralkar said he didn't see any activity until 120 hours of processing, and he processed for, say, 200 hours. Now, the interesting thing that I observed when I looked at the material was there seemed to be other elements in there. Now, this is unexpected by Suhas Ralkar. He was really using this as a process to try and mill the stock materials that you could easily get from suppliers down to his target size of 5 micron. However, when we were looking at it, we're seeing lead, zirconium, niobium, and tin sort of off on the bottom there. Where are they coming from? And we're not just talking point samples. If we go into this and look at this in a new tab, we'll see that they are mostly large area samples that were done. And we did a lot of samples, and basically lead is appearing. We've got 55% here and 48% and so forth, 45. This is 57%. A lot of zirconium and so on. So essentially what I'm saying is that it would appear that there is some production of heavier elements that are zirconium and niobium and also lead from the lighter elements of carbon and oxygen and hydrogen and nickel and titanium that are in the starting feedstock. Now, if we look at this table, which we've looked at a number of times, essentially the elements that are put in are over here, so titanium, nickel, and where is it? Oxygen and so forth, hydrogen. And the elements we're observing are this lead, which is all the way over here. Now, that isn't the only thing that we observed with the echo fuel. We observed a range of different types of strange radiation. And here's a number of different ways that we observed this. We took some 10 by 7 inch film at 400 ASA, old school type film, and we exposed that over a long period of time, and we saw a range of tracks from one of the samples. Now, not all of the fuel samples, all of the samples that were provided seemed to produce tracks, but there were some tracks observed. So you've got the periodic kind of zigzagging going on here, and the periodic kind of shapes that are bending in this case around a sort of curve. This was on the PET bottle in which the fuel was stored. This is a piece of PET plastic that was at a distance from this bottle that also was affected and observed by laser microscopy. This was a Logitech 910C that was masked, and it was using a program called Cosmic Ray Finder. And this would appear to be a strange radiation single sort of track segment that went across. This went across it, but kind of like this is kind of rotated, so you're seeing part of this M, but it's cutting through at a different plane. And this kind of looks like a shoulder sort of donut shaped with 3 segments in it and a tail, like almost like a comet going across the sensor. And this was actually the fuel when it was taken out of the PET bottle, and where these tracks had gone, the caustic nature of some of the fuel elements had etched its way through, and it was incredibly brittle, as we showed in a different picture previously in the year. But where this was contacting, we saw these spheres at various points around this area that had kind of fallen away. There was another sphere here, and there's a video that's all linked. All this information is linked to from this presentation. But from these spheres, we see these kind of tracks either coming to or from these kind of central points. So very, very interesting. 2 aspects to the fuel. One is the apparent synthesis of heavy elements that is seemingly topping out at lead, but not going beyond sort of 60%. So in my view, the lead in this case was reaching, if it had gone further and much more energy was put in, then perhaps it would have pushed out further than the stable element here. Maybe it would have pushed to bismuth before moving on. Anyhow, are there other similar experiments out there? Well, I've hinted at a few over the course of the last year, and one of the first ones which I'll bring up is that of the work of LeClair et al. At Nanospire in the USA. And he was using cavitation, and I don't know exactly if it was exactly the same. I mean, maybe laser or sound, but Cavitation was the key. I don't think he was putting in particular fuels, but he had, for instance, aluminium perforated sheet. So there was definitely not only water but also aluminium in there, and he talks about carbon being in there. So there are some similar elements. Certainly the water and the carbon are similar. And essentially he's definitely with the aluminium, maybe a steel container, but the aluminium perforated drum, and the water and the carbon, so forth. He's synthesizing again using light elements, but you can see here this incredible peak of lead. Also, you can see there's a little bit of tin coming in here, and zinc and copper and iron in that first kind of trough here, the zinc and copper and iron. And also there's a peak here at niobium. Zirconium's not particularly strong, but remember he's coming from here with the elements he had and stepping across. But it's very, very clear. Now, the other thing that he did observe was these tracks on various different materials. So, just summarising, he observed abundant lead production, wide-scale transmutation, and repeating tracks on a range of materials. And he said very clearly it was easier to make lead than gold when he was asked. And I've got a link to the interview where he said that on the Smart Scarecrow show. Now, another example would be SVA Dominque Proton 21 lab in Ukraine. And this is a chart, and he says, I'm summarizing here, Dominque observed abundant lead production, wide-scale transmutation, and new kinds of radiation tracks, specifically on the interface between conductor and dielectric. So, he used an intense electrical discharge into a rounded end-shaped fine anode of pure metal. And here's kind of a close-up of some of these tracks. Again, you've got these kind of M or zigzaggy repeating elements. As you can see, some sort of repeating elements with gaps, repeating elements with gaps. And up here, this is the M. We've got repeating elements here, repeating zigzaggy tracks, and so forth. So he's observing those same kind of transmutations. He's observing also these periodic tracks of what they call new kinds of radiation. And they used this kind of detector. So this is the experiment. It's a kind of like a discharge focusing experiment. And the actual action happened where all the discharge was kind of focused on the end of this ovoid-shaped tip on the anode, and this section in here would blow out. This metal would be unusually split, and at distance of 10 centimeters in this case. There would be aluminium, and interestingly, aluminium is the most effective material and often used by Hutchison. It's the fourth most conductive element, as I talked about in India at the early part of last year. And Shoulders notes that when you get what he considers the active agent, the exotic vacuum object, when that tries to cross an impedance change, it just doesn't like doing it. In fact, he used aluminium oxide to guide EVOs in his EVO production devices. In here, we have the piece of aluminium and then silicon dioxide and on silicon. They call this a metal dielectric semiconductor structure. And this provides a very, very good detector, it would seem, because it has this material combination that provides some impedance changes. So behind the extremely conductive and easy to transmute, according to the observations that I've done on Hutchison samples, where you see the aluminium forming iron, copper and zinc. They also have a thin pump oil layer on here, so that you've got a source of hydrogen and carbon to aid any transmutation. So it really looks like they knew what they were doing when they designed this detector, and this is something that people can learn about as a type of detector. Okay, so in the past year we found that you can use PET and just use a laser microscope, and we've also shown that you can use film rather than X-ray film, and we've also shown that you can use standard CCDs. I have to say, as a warning, I do think my Logitech 910C was damaged permanently. Some of the pixels appeared to become hot after long-term exposure to echo fuel, and that's something to consider. You need to sacrifice it. But what I want to do is try and work with the programmer of Cosmic Rayfinder to allow multiple cameras to be in the same computer, so that you could have 4 times or 8 times the chance of observing any strange radiation coming out from a sample and capturing it real time. So essentially what we're seeing in each of these cases is production of heavier elements and specifically large-scale production of lead in combination with these kind of what I'm calling strange radiation tracks. And these seem to be, I would say, the telltale that you are able to create active material, or you've gone through producing a process that is able to transmute matter. Now, I want to come on to this, which is what I'm saying is the mystery of the missing tungsten. Now, I'm going to read it straight. When the MFMP first reported the elemental composition of the part processed echo fuel ascertained by Masaryk University SEM operators to Suhas Ralkar, there was shock and disbelief. The high concentrations of lead, zirconium, and niobium especially, and traces of tin made no sense. The whole purpose of the ultrasonic processor, as I said before, was to reduce the grain size of the source metals to around 5 micrometers. It was postulated that due to the high natural critical temperatures of niobium, lead, and tin, in addition to the titanium that was in the inputs, the system was favouring highest temperature elemental superconductors. Of course, it's still very low. So, niobium sort of 9 point whatever Kelvin, and lead's like 6 or something. But, these are almost the order of the highest temperature elemental superconductors. I posited on the 9th of June last year a possible explanation for this was that the active agent may be atomizing the elements, in which case there is no lattice to support thermal vibrations, and so the actual temperature may be in the low single-digit kelvins in the range these atoms superconduct. And this concept was presented at ASTI on June the 9th. There's a presentation link there. I derived this idea essentially from the work of David Hudson, and I talk about him in the presentation. Now, Suhas also claimed that tungsten was added to the raw materials to act as a milling agent. Now, that would be, it's very hard and heavy, and it's to smash the other components together in order to make them smaller. And he learnt this as it's a standard process that people do to do just this. However, we didn't detect any tungsten in the process material above the SEM's certainty threshold, 0.1% in places and then only in some samples. And I can honestly say that at the time I thought it must have been emitted from the inputs of the samples that we reviewed. However, when I was writing this blog, Suhas wrote on a public forum, "You surely remember my telling you our tungsten powder-based ultrasonic milling during the fuel preparation and then allowing part tungsten powder to remain in the fuel." Okay, so he's reminding me, but we didn't see it. So what's going on? We have a situation where tungsten, if it was there, had disappeared, and lead and zirconium have appeared in abundance with traces of tin. So I'm asking the question, does the Alexander Parkhomov data, along with the atomic volume notion, help us to explain what is actually observed? So I've just put forward this proposal here where from the sort of George Ohsawa reactions, 2 oxygens go to sulfur. There's 4 outcomes, and the most likely is with the most common isotope of oxygen, 16, going to sulfur, 32. Now, if you take sulfur plus tungsten, so if we look at the atomic volume, we've got sulfur here, and we've got tungsten all the way over here, and we fuse those, we get zirconium and tin. Okay, 33 reactions, 15 with sulfur 32, which is the most common product of the oxygen-oxygen reaction. And all of the isotopes except 112, 114, and 115 of tin synthesized, which incidentally have the lowest natural abundance. So these ones that are not synthesized by this process have the lowest natural abundance. Then what I'm saying is these are net positive. So you've got 16 to sort of 16.5 to 28.3 mega electron volts out of these fusions. Here we have 97.6 to 107, so a lot of energy produced by this potential reaction. And if you look at it, it's the same old story. You have sulfur, which is here, you have tungsten, and they are fusing to zirconium and tin. So there's a huge shift here, and that's a really large output from this process. Combine these together and you're sort of getting something in the range of about 120, maybe 115 to 135 or something going on here, depending on which isotopes and so forth are there. Now, what I'm saying is when the system is trying to get to a stable state, which is in these low atomic volume areas, so like osmium and ruthenium, palladium, rhodium, nickel, and so on, aluminium here. It's trying to get to there. However, if you're pushing it too hard and there's too much energy being pumped in the system, and in this case maybe yielding too much energy, then the system wants to maybe balance out. And I've actually got this reaction in reverse. So if I click on this reaction here and I open that in a new tab, this particular reaction is I've got here argon and lead is going to tin and tin. So these are the 17 reactions where you get tin and tin out of reaction of argon and lead, and they're various isotopes. And if you're going the other way, I'm suggesting that it's taking 127, 128 or so mega electron volts to push this in this direction, where you get lead and argon produced. And so what I'm saying here is argon off-gassing may prevent a reversible reaction. Tin isotopes are not produced in this reaction, are not needed. So 112, 114, and 115 do not appear in these reactions where you have tin and tin going to lead and argon. And so they're not needed. And in addition, tin 117, which is produced in this reaction, also is not used. And potentially, this might be the reason why we have these kind of trace amounts of tin appearing here, SN here, SN here, which are below the detection threshold. The zirconium essentially could form the niobium by taking hydrogen out of the water. So your two oxygens are making sulfur. Your hydrogen and zirconium is making niobium. You can also have calcium, which is formed by various George-Joshua paths going to zirconium. So the relatively high levels of zirconium seem to be really relatively easily explained. So you have like 7.9 by weight and 8.3 by weight. And when you can, this is 8.2 by weight. When you consider that lead is much heavier, then this is actually quite a lot of zirconium that's coming out of the process. So there are various paths to zirconium. However, if you actually take, hydrogen or deuterons plus carbon, you go to nitrogen, and hydrogen and deuteron plus nitrogen goes to oxygen. So you can end up breeding more oxygen for various reactions. So what I'm suggesting here is these kind of reaction pathways can explain the presence of the zirconium, the tin, the lead, and the niobium. So, in summary of this, if the eco-fuel preparation reaction path is as above, the W would be converted to isotopes of zirconium and tin, reaction 2. All of the tin isotopes that are produced are used to synthesize lead and argon, except 117, and that might account for the small residual amounts of tin. The overall reaction might not be reversible, as the argon produced might leave the water reaction, or because it is noble, not conductive. So what I'm suggesting is that the reaction's going on in here, but it's off-gassing the argon that's produced, so it can't go back, and so you get kind of like a build-up of lead. And all isotopes of zirconium are produced by reaction 2. However, zirconium can also be produced by fusing 2 calcium atoms, with one source of calcium atoms coming from George-Oshler reactions. Also, there is 16 oxygen plus 204 lead. So the 204 lead that's synthesized can go to 96 zirconium. That's more zirconium being produced, plus more tin. So this is a reaction here that's extremely energetic. I think it's like, let's have a look. I think it's like one of the most energetic reactions that there possibly is with lead. So if I actually take out, this is 143.9. If I take out the oxygen there, it's actually the most energetic, right? So this is very favourable for oxygen to combine with lead to produce zirconium and tin, these specific isotopes. And with the 2 times this tin that's produced, you get more lead and argon. So it's like an iterative process that reduces the amount of 204 Pb and leads you to a skewing to the heavier elements. And this is actually what you see in nature. So if I actually take the Pb here and you look at the isotopes of Pb, we can see that 204 Pb is only 1.48%. So, could it be that some sort of similar process has gone on in nature to produce the isotopic ratios? So we're starting to see how this process, if it is this kind of process, is explaining the isotopic ratios of tin. So if I go to tin again, I did this earlier on in the video, but we'll look at tin. So we look at tin, and there's almost none of the isotopes that it doesn't produce, that reaction doesn't produce, these 112, 114, and 115, yeah, very, very low percentages, fractions of percent. And then also, so tin and lead isotopes. Okay, the abundance of zirconium produced could lead to the observed niobium, because there's so much zirconium, and because I'm saying that the active agent is able to produce reactions that have a favourable direction, and of course going from zirconium to niobium is a fairly large change in atomic volume. It wants to do this, and hence they're energetically favourable. If you actually look at how much we're getting out of that, so open that link in a new tab, you're getting 12.4 and 5.9 depending on whether it's D or H, going to isotopes of zirconium. So it's energetically favourable to do that, given the presence of hydrogen reaction 7. The small amount of silicon observed in one sample area could be due to the standard Austrian reaction between carbon and oxygen. The proposed reaction considers the energetically favourable nature of the individual steps, with all but Sn plus Sn to argon plus lead reaction being net positive. It is my hypothesis that this is a hard-driven reaction. And in fact, I would say that this reaction, the one of Adamenko, this reaction of LeClair and the Suhas fuel processor are all really hard reactions, and I would suggest that the Suhas fuel processor is less hard than either the LeClair or the Adamenko, with Adamenko being the most extreme. So this is an order of extremeness in terms of synthesizing the active agent and forcing it to do work. In the case of Adamenko, he produced super heavy elements, transuranics, and elements that don't even exist in our solar system, galaxy, or near universe. So, he was definitely pushing it towards the limits. So what you're actually looking at here is kind of almost a nuclear battery, in that it's actually able to store energy into heavier nucleons, and then the actual active agent that does this is also able to release that energy potentially at a later time. So I'd like to say here that in both Bolivian and Cornish tin oxide seams, it should be noted that wolframite is also found, and wolframite contains tungsten, wolfram. So looking at nucleon exchange reactions and fusion and fission with lead, out of all of the reactions that Parkhomov has given us, well more than 500,000 reactions, the one given above is the fourth most energetic. And if we consider that the Earth's crust gives us billions of years of experimental evidence, then the observation of tin with lead is not surprising. And then we can actually look at the other elements that are found with lead commonly. So tin and antimony. So if we look here, open link in a new tab. So we have chlorine and lead goes to cadmium and antimony, but potassium and potassium with lead goes to tin and antimony. Calcium and calcium, and you can breed calcium from potassium with a hydrogen atom. You can get antimony, and with potassium here again, tin and antimony. And looking at this, where you have, SN and antimony here, they're right in the middle of the table, and it's kind of like, it's almost like they're splitting in half almost. Now silver, which is found, that has favourable nuclear reactions with lead, and again we have chlorine here. So here we can see you have various reactions producing silver, and in the case of potassium with lead, you're getting silver and xenon. And you can go through the list and explore the data that I'm sharing here. Lead is often found naturally as galena or lead to sulfide, PBS, and there are a number of exchange reactions that yield tin from sulfur and lead. So we look at those. Again, these are energetically favourable, rudely energetically favourable, 129 megaelectron volts nearly, 11 reactions, and a lot of them producing tin here with sulfur and lead. However, it must be noted that sulfur is just 2 times oxygen as per George Joshua. So you could have a situation where you have one sulfur atom with 2 lead atom nuclei, and they're breeding O plus Pb reactions, and the O plus Pb is producing tin, lots of tin, and it's producing zirconium, but zirconium, as we said, is just double calcium and so forth. So it's a little bit more complicated, I would imagine, and this is something that we recognize. So I'm suggesting that, if you wanted to, you would have a reactor with molten lead oxide electrolyte yielding 75 reactions, 25 of which exceed DD fusion. So let's have a look at that. So here's our 75 reactions, and a very large amount producing large amounts of energy. In this case, these reactions here are producing krypton and xenon. So lots of noble gases being produced by this reaction. It would be ideal with the active agent in it stimulated or nucleated and controlled. Use of molten lead oxide and discharges with electron promoters is exactly what is in the Ukrainian Boris Vasilyevich Bolotov's 2001 priority patent, as previously discussed in the blog post on making gold. Let's have a look at that. So here it is. He's warming it up. He's doing discharges. These are the pulses, and if you go into it, he does suggest using lead oxide in there. The most energetic reaction is 12 carbon plus 204 Pb goes to krypton and tellurium here. And what I want to say is, it is interesting to note that without Suhas Ralkar actually intending it to, the ECHO reactor has lead in addition to carbon and oxygen. And we have established that it has the active agent in it, and it produces copious amounts of strange radiation, even long after production. So the fuel sample that produced all of these kind of strange different effects on various materials and different detection methods, it was doing that months after it was produced. And so it doesn't just end straight away. Furthermore, the alchemists also often had lead, carbon, and oxygen in addition to potassium, which is an electron donor stimulator, in my opinion, for the active agent production in their experiments. So, again, we're seeing that the alchemists were doing the right thing given what we're learning here. What I'm suggesting here is that because we didn't have billions of years of processing of the elements in situ, that the lead might not be at the perfect isotopic ratios as found in nature. So it might be really important to do a mass analysis of the lead that we have observed there. Again, zirconium is double calcium, and that patent by Bolotov says this: the inventors also noticed that zirconium was related to calcium. Within the Earth's crust, zirconium is synthesized from calcium oxide as follows, and consequently zirconium dioxide was referred to as double calcium oxide. I also want to put in here that we've previously discussed the production of zirconium in Lion reactors, and so it's quite clear that the appearance of zirconium is an important sign of Lena reactions. As I said above, there's reactions between aluminium and phosphorus that produces silicon, and Bolotov actually had another patent to claim production of silicon using aluminium and phosphorus, and we can see that the second and fifth most energetically favourable reactions are conversions of aluminium and phosphorus to silicon and silicon. Let's open that up in a new tab. So here we go. When we take aluminium and phosphorus, you have here silicon and silicon produced, and silicon and silicon produced. And this is where I want to introduce the notion of where if you're not driving the process extremely hard, you may be able to target a particular outcome. So what I'm saying is that the active agent that is able to reorganize the matter, if it's not forcing it so hard into one of these atomic volume wells, then you might find that certain levels of energy imbalance will favor one particular production path than another out of the available production paths that can happen. And what I'm just saying here is this is all of the reactions for aluminium and phosphorus, and you get them there. And as I said, second and fifth produce just silicon and silicon. So what we have is a claimant that has made two claims that the data in the fusfis.org tables from Alexander Parkhomov support. The patent says, a method for producing silicon comprising the production of high-pressure elemental silicon from chemical elements of aluminium and phosphorus by the action of electric current of density greater than 111 amps per meter squared. So he's even specified it there. So, like many researchers, high electron density precipitates the effect. One researcher, Kravitz Key, proposes the use of 7 to 10 kiloamps at 1000 volts. I guess these might be pulses with a frequency of 450 kilohertz. Is this an ultrasonic frequency in addition to these pulses? So it would be something like the fuel or foil processes from Suhas-Ralkar. So it does have similarities to both the work of Adamenko and Ralkar, this work by Kravitz Key. Again, he's saying massive transmutation production. Now I want to say, given the evidence above, what, in my opinion, at this stage, new fire fuel is. The implications of this work is that the new fire Lena fuel has to have 1. The active agent plus elemental feedstock. It's not just the elements that made the active agent, which may include some of those in the elemental feedstock. What I'm saying is that if you do not have the active agent, you will have no Lena reactions. Now, Piantelli told us you can make the fuel externally to the reactor or in the reactor, and he did both. To me, this expressly implies that the elements themselves are insufficient. Many people have tried chucking the elements into a box, warming them up and going, I don't see any reactions. I believe this is why. Me356, Suhas-Ralkar, Homlid and likely Rossi make it externally. They didn't necessarily always make it externally. They may not be making it externally in some embodiments. It is the natural thing to do once it is understood at least on the cause and effect basis. Because really, from a commercial point of view, it makes sense to not have the sold reactor able to produce the active agent. Moreover, you would engineer the sold reactor to cause rapid degradation of the active agent if the sold reactor is tampered with. In this author's view, simple contact with water or moist air would be adequate. Hutchison guided the nucleated active agent to the work area and grew and manipulated them there in metals or in the surrounding areas. Eagerly, Adamenko and others made the active agent in the reaction zone, and then they stimulated it at the same time. Shoulders did both, and you know this because he says he can store it in metals indefinitely until he intentionally put it to work. In the case of Echo, when you have the seed fuel that has the active agent in it, I think you could add more lead oxide, and then you could use the lead oxide as a feedstock to enable longer duration reactions. Targeting valuable metals. Well, we've already started to discuss the production of gold, but I'd like to look at another valuable metal. So let's looking at iridium, which is about, at the time of writing this, it was $43,300 per kilogram. By looking at the atomic volume chart and taking the view that the process is an implosive one, we know that we will need an element that is above the mass of iridium, that has as high atomic volume as possible, and one that is right at the other end of the periodic table, preferably again with high atomic volume. The most favourable reactions will be those that can lead to the lowest atomic volume of the solid liquid products whilst maintaining stability. That these will yield the most energy output may mean that under the right circumstances, the overall net energy balance may be positive. So we need something. Our iridium is down here in this last pit before the radioactive pit of uranium. So we need something that's above this, and we go up and we want it as high as possible. So the highest possible, which is technically stable, although it is unstable, is bismuth. So we have Pb and bismuth here. And then we want something all the way down here. And ideally we want something that's good as an electron donor. So I would suggest something that is, typically like potassium or calcium, an alkaline metal. And we want something that has really high atomic volume. So calcium here and potassium here. So these are the obvious candidates with this understanding. Bismuth over here, lead, calcium and potassium here. So what do we actually see? Now, bismuth is really favourable, really, because it has low toxicity. It has a low melting point, and for a kilogram you're looking at $10 to $25 at the time of writing. Okay, lead's much cheaper, but when you're talking about $43,300 per kilogram, you want a reaction that's going to produce a higher yield rather than to quibble about a few dollars here and there on the feedstock when the output is worth ridiculous amount of money. The other thing about iridium is its stupid high temperature that it melts at. So if it is produced, then it will come out of the molten bismuth or the molten lead. So let's look at those reactions. So an element with bismuth leading to an element plus iridium. And what do we get here? Bingo! Calcium plus bismuth leads to iron plus iridium. Iron plus iridium, what are we looking at on the volume charts? Iron all the way down here. We know that's favourable from an energetic point of view. And iridium here. So we've gone from calcium and bismuth, and it's gone boom. It's done an exchange to go boom and fall into their respective nearest wells. What are we looking down here? Sulfur and bismuth. Okay, so sulfur is classic alchemical element. Of course, also calcium can be bred from potassium. And so calcium, sulfur and bismuth rather, titanium and iridium. Looking at lead. So again, there we go. Potassium and lead goes to chromium and iridium, potassium and lead, chromium and iridium, calcium, calcium, potassium, chlorine. So, like, potassium chloride or calcium, so on, mixed with lead, we're getting some really favorable reactions. These are 35.7 sort of, and these are 45. So, this is why the alchemists use bismuth. It is more energetically favorable to do these reactions, and this is a great reaction here, iron and iridium. Both iron and iridium have much higher melting points than calcium and bismuth. So you could expect these to just basically precipitate out of your molten material. Rhodium is even more valuable. At the time of writing, it's nearly $72,000 per kilogram. So perhaps voltage biased, high current voltage, high frequency discharges through molten lead chloride might yield valuable precipitations of rhodium and an evolution of xenon gas. Let's have a look at that. So chlorine plus lead, so lead chloride, PbCl. Deal with that. This is actually with the isotope of 204, leads to rhodium and xenon. Again, that might off-gas, the rhodium's high melting point, and so on. So that this looks a bit dangerous to me. You've got some chlorine, which is not good. Lead, I wouldn't particularly want to do this. I'd like to stick with the bismuth and kind of like potassium or calcium reactions. And that's right at the top of the tree. But look how energetically favourable that is. It's ridiculously energetically favourable to do that reaction. So I'm saying here it's not the reaction that an average lab owner should do. Another option might be discharges through zinc and lead. Let's have a look at that. So zinc and lead 204, rhodium and holmium, but is not so energetically favourable. So, my conclusion. I've already written about some of the physical observations one can look for both during an experiment and after that indicates the presence of the active agent in the actual reaction that went on. In the view of this author, feedstock choices depend on many factors, some of which in no particular order are electrical conductivity, electronegativity, melting point and miscibility of components, strength of the active agent, the driving intensity and resonance relates to the level of the implosive action and targeting, the net atomic volume of solid liquid products compared to the feedstock, which is related to the energetic favorability of the product balance in most cases. By having an idea of the output elements desired, one can use the data provided by Dr. Alexander Parkhomov at fuzzfizz.org to establish potential reagent element phase choices for the process to target an element. Now I just want to talk about a few experiments and natural things that I believe have the right components to exhibit the process which I call the new fire. The active agent can be made, stored, grown, harvested, used and abused in a variety of ways to affect excess heat, light, electricity, particles, transmutation and more. For examples, as shown above, the active agent can be advantageously used with element combinations that lead to desirable energy or element production. Choice of isotopes to use as feedstocks with the active agent would depend on physical parameters such as pressure, temperature, corrosiveness, phase, electronegativity, etc. Also, as I said just above, the amount of drive may target a particular element, that being the kind of electrical intensity, but also resonant factors, either phonons or electromagnetic. So, first up, natural lightning. Make and break in bolt. That's the active agent. Make and sustain in persistent ball lightning. Organic life. It synthesizes the active agent or captures and uses very small active agents in, for instance, going from manganese 55 to iron 56 or going from potassium to calcium. Mexican alchemists. They harvested from the environment and deployed. They had these metal bowls out in the sun. The sun was the right temperature, captured from the environment, and then deployed the active agents and maybe grew them and used the reactions that we've talked about in this and the previous video. Tesla harvested them from the dry, this is important, Utah environment and made the active agent. So he did both. Henry Murray harvested from the dry Utah environment and grew the active agent. And when I'm saying growing, I'm very specifically saying it's growing a little bit like the Dyson air multiplier. Like it's kind of like you feed it and it has a self-gaining process. Tesla talked about this. Boris Vasilyevich, he made and destroyed the active agent in an instant. When you have a discharge, given the right parameters, frequency, intensity, there are opportunities for both making and breaking the active discharge. Joseph Papp, he made the active agent externally for first patent and internally to the reactor for latter patent. He grew them and harvested them in a cyclical fashion once they were in the reactor. George Joshua made and destroyed the active agent in an instant. This is the carbon arc explosions between two carbon rods, either underwater or in air. John Hutchinson guided nucleative active agents to zone where they were grown and manipulated. A typical transmutation that we've observed in our samples from him is aluminium and aluminium to iron. Kenneth Shoulders, he made, grew, stored and deployed in apparatus using, say, mercury and krypton. Mercury and krypton, let's have a look at that. So, mercury and krypton, there's, in this particular configuration, there is 1,401 potential reactions. Mercury, krypton, cerium, 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 barium, neodymium, and so on. So, mercury wetted tungsten electrode, producing the EVOs in a krypton environment, krypton being a good gas, for noble gas in a discharge environment, in low pressure discharge environment. Really high energy for this favorable reaction. Alexander Chernetsky made, grew and destroyed an apparatus with some ancillary effects of destruction observed. So it is absolutely clear to me that he was producing strange radiation given the observations that he claimed, and also evidence of cold electricity. He was definitely producing the active agent. Pons and Fleischmann, they made, grew and triggered, and their major example, the 1cc singularity in that it's known as, this 1cc that apparently formed a ball lightning, it would seem, from the damage reported, and vaporized a large amount of material in their lab. They made, grew and triggered this. Francesco Piantelli made, grew and harvested, Canon patent, made and then deployed active agent in cell. In what I call the German patent, they made, then deployed the active agent in the cell with deuterium and xenon. These are both optimal in their own right for construction of the active agent in the gaseous phase, leading to DD fusion. Deuterium plus xenon is less energetically favorable. Let's look at DD fusion. So DD fusion here is leading to helium and 23.8 MeV. Look at D plus xenon, open a new tab. This is only 13. So given the fact that you have the discharge in a D and xenon, deuterium and xenon environment, the most favorable outcome is this. It's actually a beautifully elegant experiment, and I have to show you this because it's possibly one of the most beautiful cold fusion patents there are, and what's even better about it is it's essentially available for you to all enjoy because of its age. But essentially, they're just putting xenon and deuterium in here. You have a thing to produce a sort of a bias, and then you do discharges, and you're getting your excess heat. Helium is coming out here, and its claims are just essentially very little. That's it. It's just beautiful. I love this. Love this pattern. There are 31 possible deuterium plus xenon and nuclear exchange reactions. Let's have a look at those. And there is a possibility here for reactions. I think two of them here, producing vanadium and germanium, and potassium and krypton. These are potential outcomes that I have a higher favorability in a nucleon exchange reaction. However, given the fact that DD fusion halves the distortion in the physical vacuum, according to Stoy and Zarg, this, in my opinion, makes it very, very desirable on an atomic volume basis. Okay, well, that's a distortion of the physical vacuum of the atomic nuclei basis. So Stanislav Adamenko, he made and destroyed active agent in an instant, and he saw a wide range of ancillary effects of destruction. Norris Peary made, grew, and overexcited to destruction of the active agent in the reactor. Andrea Rossi made active agent in cell, likely first with good old alchemical choice of potassium for lower temperature activation, then later lithium for higher temperature operation and better yields, in combination with aluminium, which has both nucleon exchange and fusion reactions to iron that can progress to nickel and copper. There's some links here and you can explore those. Francesco Celani, he made, grew, and sustained in the wires, so it's very similar to Francesco Piantelli. George Eagley made, grew, and overexcited to destruction in his Nova reactors. Leif Homlid made and fed the active agent and observed breakup. Suhas Ralkar made, grew, and stored active agent in metal fuel externally, cyclically grown, harvested, and destroyed in the reactor. Anatoly Vachev, similar to Bolotov's 1956 work, made and destroyed the active agent in an instant. When I say that, these are kind of like discharge experiments. Clean Planet, Mizuno, similar to the Cannon patent, but it's a simplification. In the Cannon patent, they build the active agent in the gas phase and then deploy it. In this one, they build it up and store it straight away in the metal and stimulate it there, and then they overexcite it to do work. The Lion reactor, if I'm saying that the Echo reactor is a softer version of LeClair, and LeClair is a softer version of Adamenko, the Lion reactor is another step down in terms of its how soft it is. But there's no doubt it has the strange radiation, it has similar tracks to Shoulders observations, and transmutation of materials, including this zirconium, as we've mentioned before in previous presentations as well. Nucleated the active agent in the core and grown over days in other reactor materials, as well as potentially in the core. So I want to thank everyone that's made it possible for me to be able to do this work. There have been some very kind support over the past few months, and this allows me to explore my thinking and to share it with you guys and try and present it in as clear a way as I possibly can. I want to really thank Alexander Parkhomov for sharing this data, and for Philip Power and Dennis Lamotte for making it into accessible online databases that you can explore. I want to note that also with Dennis Lamotte's work that we put at physvis.org, there is a GitHub where you can download the data and the application, and you can actually install that locally so that you don't need to be online to use this data, and that might be useful for those people that want to use it in other settings. If you feel that you've appreciated this work and you think it's important that we be able to continue to explore this, It would be very helpful if you can consider donating. And at the bottom of this blog post, you can see various options. So again, thank you for your time, and I look forward to your comments.